In this lesson, we're going to talk about solving logarithmic equations. So in the previous lesson, we talked about exponential equations. In this lesson, somewhat similar, but we're going to be working with logs. So the steps here are that you always want to combine all the logarithms onto one side of your equation, and then use log laws to simplify them. And the other side of your equation, you want to be a constant. You then will change from logarithmic form to exponential form, and then you'll check using your restrictions to determine if your solutions are valid. So if we look at the first example, you'll see here that we've got log base 2 of x equals 3. Now the thing to remember is I made a little note here, is that we want this x to be greater than 0. So if you look here, if we look at x, we know that x needs to be greater than 0. Now in this case, all the logs are together. Solving this one is quite simple. We just need to change it into exponential form. 2 to the power of 3 equals x, which means that x is 8. And we can't take the log of a negative, so that's why our restriction is x has to be greater than 0, and 8 is greater than 0, so this is a good solution. For question B, we've got log of x plus 2 plus 1 equals log 50. So the first thing I've done here is looked at the restriction. Here, x plus 2 has to be greater than 0. That means that x has to be greater than negative 2. I like to do this right away at the beginning, and then when you get to the end, you can just compare your solution and make sure that it fits with your restriction. So from there, I'm going to start solving. I'm going to gather all the logs onto one side of the equation. So I subtract log 50 from the left side, and then I subtract 1 from the right side. So I get log of x plus 2 minus log 50 equals negative 1. Then I used log laws to combine these. So x plus 2 divided by 50. Because this is subtraction, we'll divide by 50. And then the other side is just negative 1. From there, you're going to change it into exponential form. So 10 to the power of negative 1, because remember this would be log base 10 because there's no base written. 10 to the power of negative 1 has to be equal to x plus 2 over 50. Then I just change this to 1 over 10. Multiply this side by 50. You end up with 5 equals x plus 2, so x must equal 3. And 3 is greater than negative 2, so we know that this is a good solution. If we look at C, just move the restrictions up here. It's a little bit cramped for space. So in this logarithm, x plus 2 has to be greater than 0, so x has to be greater than negative 2. And for this one, we've got x minus 3 has to be greater than 0, so x has to be greater than 3. When you have two restrictions like this, you need to determine which restriction encompasses the other one. So in this case, if a number is greater than 3, it is definitely greater than negative 2. If it's greater than negative 2, it's not necessarily greater than 3. So how you can think of this is that the x is greater than 3, that restriction wins out over this one. Because if a number satisfies this restriction, it will for sure satisfy this restriction. So the restriction on this equation is x has to be greater than 3. Now in this case, the logarithms need to be moved to one side. So log base 4 of x plus 2 minus log base 4 of x minus 3. I just subtract log base 4 of 4. Then I'm going to simplify this into a single logarithm. So x plus 2 is on top. This is subtraction, so x minus 3 goes to the bottom, and 4 goes to the bottom. I then change this into exponential form. So the base of the logarithm becomes the base of the exponent. 4 to the power of 0 equals x plus 2, and then I just multiplied this through, so 4x minus 12. 4 to the power of 0 is 1, and then you bring this up. So 4x minus 12 equals x plus 2. And solve for x. X is 14 over 3, which is greater than 3. So this is a good solution. If we go over here, you can see here our restriction is x is greater than 3. In this case, the logarithms are already on the same side of the equation. So I just used log laws. These are being added, so that means I can group them together using multiplication. Then I change into exponential form, so 10 to the power of 1 equals x times x minus 3. Then, because this is a quadratic, I know that I need to move everything to one side and factor. So in this case, I get two solutions, x equals 5 and x equals negative 2. But my restriction was x has to be greater than 3. So only x equals 5 is a valid solution. And then in example E, again, I need to move all the logarithms to one side. So you can see I moved log base 2 of 3 to the left side by subtracting. I then simplified using log laws, so x minus 2 times x and divided by 3. Changed to exponential form, so 2 to the power of 0 equals x minus 2 times x over 3. 2 to the power of 0 is just equal to 1. So when I multiply by 3, I get 3 equals x squared minus 2x. Again, I have a quadratic, so I need to factor. And here my restriction was that x had to be greater than 2. So only x equals 3 is a good solution. Make sure you show both solutions and then just cross out any that don't work. On this next page, we sort of have a mix of a few different things. So in this case, we're looking to solve for a missing variable. Now, if you think way back to the beginning of this unit, I talked about how when you have a variable in the exponent, if you're not working with perfect squares or perfect cubes, it can be really hard to solve for that unknown. And that logarithms were going to help us with that. So this first example is a perfect example of that. Here we have that 7 to the power of x plus 3 is equal to 1. Well, we know that anything to the power of 0 is always equal to 1, so you could use that fact right away. What I did was I actually just changed this into logarithmic form. So log base 7 of 1 is equal to x plus 3, which means that x plus 3 has to be equal to 0, and x has to be equal to negative 3. Similarly, you could solve this just by getting the same base, because 7 to the power of x plus 3 would have to be equal to 7 to the 0, because that's equal to 1. And then you could set x plus 3 equal to 0. So a few different ways that you could solve this problem, and that's true for a lot of these logarithmic and exponential equations. If we look over at question B, you've got a log now in the power. So the key here is that you need to first evaluate this logarithm. So the power is log base 2 of 4, which is equal to 2, since 2 to the power 2 equals 4. So then you can just replace this logarithm with 2. 4 to the power 2 is 16. Down here, we have a logarithm within a logarithm. So again, in this case, what I did was I actually changed between forms. There was nothing in this logarithm that I could solve as is, so I changed log base 3 of log base 2 of x equals 1 into exponential form. 3 to the power of 1 equals log base 2 of x. And then I actually changed it into exponential form again. So 2 to the power of 3 equals x, which means that x equals 8. So I just used the changing of forms twice. This one is a little bit messy, but again, if you change it into exponential form and then solve, it works. So here we've got x to the power of negative 3 over 2 equals 8. You can then rewrite this as a root, so the square root of x to the power of negative 3. You can then get rid of this negative exponent, write it in the denominator, and then bring it up and multiply the other side by the square root of x to the power of 3. Then we can change this to 1/8. The reason I did that is because I knew that 8 was a perfect cube, so it would be helpful to have this on the other side. I then squared this side to get rid of this square root, and then I took the cube root of this side to get 1 over 4. So a lot of steps there. Sorry, off the camera there. A lot of steps here. There is certainly other ways to solve this problem as well, but just flipping between forms and remembering all your exponent laws and log laws is going to come in handy. Now, sometimes you're going to have exponential equations that you need to solve where you can't get a common base. So this is when we can take the log of both sides. And from there, it's going to be really similar to what we were doing in the first few examples. So your steps are written out here, that if you have an exponential function where you cannot get the bases to be the same, what you're going to do is take the log or natural log of both sides. You'll then simplify using the log laws, just like we did before, and then you'll isolate the variable. And from there, you're actually going to use your calculator. So these examples look a little bit long. Oops. But basically here, these are similar to what we had done in the last lesson. 5 to the power of x equals 40. But in this situation, we cannot make the bases the same. We cannot have 5 and 40 both written in terms of 5 or any other number. So what we're going to do is take the log of both sides. So I'm going to take the log of 5 to the power of x. Remember, from log laws, the x will come down in front. And I'm going to take the log of 40. From there, you just need to get x by itself. So we're going to divide by log 5. Once you're at this stage, this just goes into your calculator, log 40 over log 5, and you'll get a decimal for an answer. Similarly, here we have base 4 and base 3. We cannot write those as the same base, so we're going to take the log of both sides. Now, I've taken the log and also moved the exponent down at the same time, so we get x log 4 equals 2x minus 1 log 3. I then separate these values. So here we have 2x log 3 minus log 3. And then what you can do is you want to get the x all by itself. So in the first few examples we did in this lesson, we always moved all the logs to one side. Now what you want to do is you want to move any logs or any terms, essentially, that have x's in them onto one side, because our goal is to isolate x. So here I moved 2x log 3 to this side, so you can see that here, and then I factored out the x. So I was left with x times log 4 minus 2 log 3. Once you have everything just in terms of log and numbers and that x is out, you can then divide the other side by this whole thing. So you'll see that there. Once you have just log and numbers, then you can plug it into your calculator to get your decimal solution. Over here, same thing. I've got 2, 3, and 5. I cannot rewrite those to be all in the same base. So again, I took the log of both sides. What you'll notice here is I've got log of 2 times 3 to the power of x. With our log laws, when I split those up, that's log 2 plus log 3, and I moved the x down in front. And on this side, I just multiplied this through, so x log 5 minus log 5. Then I moved the terms that had x's in them to one side, and the terms that were just logarithms with numbers to the other side. So we have x log 3 minus x log 5, and negative log 5 minus log 2. I factored out the x, and then I divided. And again, you're going to put that in your calculator to get your solution. E is very similar. Again, I took the log of both sides, brought the exponent down, so x minus 5 times log 19, x plus 2 times log 3, moved the terms with x's to one side. Sorry, first I split these up, so distributed, then moved the terms with x's to one side, factored out the x, and used division to get my solution. I think I skipped skipped an example here. I skipped C. This one actually doesn't require logs. This could have been in your exponential functions lesson, so I skipped it, but it doesn't actually require logs. Okay, question F. This one, again, has a log within a log. Again, this one's a little bit different because here we can rewrite this in exponential form, then simplify it a little bit, then write it in exponential form again, and your solution actually comes out quite simply. So this is very similar to the previous page. Same thing over here. Our first step is to write this in exponential form. 5 to the power of x equals 40. If you notice, that's actually the exact same question as part A on this page. Now we can take the log of both sides and move the x down, and then divide by log 5 to get our answer. So what's really essential with these questions is that you sort of have this big toolbox full of tools, whether it be changing these into exponential form, trying to get the same base, taking the log of both sides, all of these things, and you sort of just need to be able to use the right tool at the right time. So they really require some practice. Finally, if ever you are trying to solve equations that involve E or ln, the process is all exactly the same. It's just that instead of taking the log of both sides, you'll take ln of both sides. So in this case, we've got e to the power of x and 2 to the power of x minus 1. Here, we cannot make these bases the same, so we're going to change this into logarithmic form using natural logs. And again, we have x ln e and x minus 1 ln 2. Just remember that ln of e is equal to 1. So here we're left with just x equals x ln 2 minus ln 2. We bring the x terms with x's to one side. We factor out the x, and we divide on our calculator. So exact same steps, we're just using natural logs instead of logs. Question B, almost exactly the same. We take the ln of both sides. So we get 2x minus 1, ln of e, which is equal to 1, equals ln 5. And then we isolate the x. Now in this case, that looks a little bit different. We just get 2x equals ln 5 plus 1. But again, you're just going to use your calculator. And finally, for question C, we've got ln of x plus 1. We're going to move this ln of x over to the left side. We're going to use log laws to simplify. And then we're going to change this into exponential form. So the difference here is that these two were exponential equations where you couldn't get the base to be the same, whereas this one is already a function that's in terms of ln. So here we're going to gather those like terms and then change it into, not gather like terms, use our log laws and then change it into exponential form. So e to the power of 1 equals x plus 1 over x. E to the power of 1 is just e. We multiply by x. And then we're going to factor this. So x times e minus 1 equals 1. And then divide. You can do this in your calculator. You could probably do these steps a little bit differently. Ultimately, you can do it in your calculator or even leave it in terms of e. That doesn't bother me, to get your decimal answer. So there's a lot in this lesson. It does require practice. There's not a lot of natural log questions in your textbook, if any at all. So I've just given you a couple here to try. Try these out. They really do require practice. And that almost is the end of the unit. So you're almost at the end.